Okay, last part of the discussion. Now that you have so many floor systems, how do you select the best one? Of course, these days the choice has almost, because people have gone through this 100 times, 1,000 times, and people have come to the conclusion that for a tall building, for speed of construction, not for cost, not for anything else, and for mechanical services and for architectural reasons, flat plate, flat slab with post-tensioning is the best system. That's almost an automatic decision in most cases. But in many cases where post-tensioning may not be possible, may not be available, or if it is not approved by the authorities, because flat plate, flat slab is not allowed by the code for tall building for carrying lateral loads. It has no frame capacity. So it cannot be used in a seismic zone without other system. So it's still a problematic. You have to prove that the system will work without the frame action. So we'll come to that later. But the main thing is span length. Basic consideration, we have to look at the span length, whether it is small, medium, or long. Aspect ratio, square, rectangular, oblong. Loads, light, medium, or heavy. We have ducts and piping, electrical, mechanical, water supply, openings, size and location, architectural consideration, aesthetics, clearance, special elements, drop panels, column capitals allowed or not, construction consideration, formwork, time, and ease of construction. So these are the list of the things that you need to make as a checklist before you choose. So this is the input data for your system selection. You have to choose what is the requirement on each group. That means this decision is not purely structural. This decision goes across all these aspects because it affects everybody, not you. So that's why when you start the selection, you need to look at all these considerations and choose your option. It's like a drop-down menu, Then you do, and then you have the first set to start with. And after that, then you can go to the next steps. Then flat plates, normally if you want to use flat plates, it is only for relatively light load, light load, common for residential building, used where drop panels or column capital is not undesirable. So once you have cleared the first list, then you can start to go to which system will fit you based on your choices in the first page. It's like a wizard, step-by-step wizard to choose the system based on your first questions. Then you go to the next step and you choose the second. These are the system attributes. Flat slabs are used, medium span, 6 to 9 meters. And then, of course, this is without post-tensioning. You can always post-tension to change the span length range. Baffle slabs are used for larger span, relatively heavy loads like libraries or storage, especially for heavy loads. And then common for public buildings, more aesthetic appearance, difficult to construct, requires special formwork. Beam slab, no. Beam dash slab and beam and slab, I told you two terms. Now is the time to clarify. So beam dash slab is when the beam is part of the slab and is carrying only part of the load and it's not acting as a support. So which means that the beam stiffness is not very large. It's just bending, it's just assisting the slab, not acting as a support. But when the beam is so deep that the slab is acting is transferring the load to the beam, and it is a true two-way system, slab to beam, beam to column, then we see beam and slab. And for beam and slab to work, this beam stiffness has to be at least 5 to 6 times more than the slab stiffness that is supporting. That means it's really, really deep. Normally, such beams are not practical. Nobody allows you to have beams which have 5 or 6 times stiffness compared to the slab that is supporting. So 90% or 95% of the time, we end up with a beam dash slab category for the system. Medium to large spans, relatively economical in concrete and steel cost, greater depth, increased building height. So there are other reasons why people will not allow you. These days, tall building, hardly anybody will allow you to use beam slab. You will find it very rare now. Except when people really want to make very economical building, height limit is not a problem. It's a residential building, and they can put false ceiling, or they don't mind about the beams, something like that. Cost-wise, still cheaper. Pure structural cost, beam slab or beam and slab is still cheaper than other systems. Band slab is a kind of a beam slab, but the beams are very, very shallow, wide and shallow beams. So they are more like stiffeners in the slab. But the beams are not shallow, but very wide. So it's like a flat slab with a stiffened portion for the column strip. It's just to reduce the thickness of the main slab further. So it's a band slab is quite popular. So medium spans, more economical, is common in industrial floors, parking areas. You will see mostly in parking areas because of the height clearance. Because parking area height is small, you need room for the cars to park, so they put band slab there. You will see often in parking areas. One-way joist and beam, this is very good for tall buildings. Many people use it still because joist, as I showed you earlier, this is a narrow beam, closely spaced, and they can do long spans. Okay, so these are very good, up to 12 meters they can go. And they're easy to construct compared to wafer slab because there's only one directional duffel, not two-way. So it's easy to make. So if the forms can be slide and removed, quick construction. So two-way, for a wafer slab, you need a pocket. So form cannot be pulled out. But for a rib, you can pull the form out from the one side and then move it up. So the whole form system can be flown out and moved to the next slab. So outside. So this is still okay. So this is just roughly frame system resistance to lateral load. So lateral load, if you are going to use the floor as part of the lateral load system, which for tall building, normally we can't. We will talk about that, why not. But we are also, this course is not only tall building, it's about buildings. So if you're designing a 10-story building, 8-story building, 7-story building, then you can see that, okay, you can mix them up like this. Okay. So you can see that if there's a low wind, no seismic zone, flat plate up to 6 floors, flat slab up to 10 floors, and then beam and slab, you can go up to 20 floors, right? Very light lateral load. If you have a high seismic zone, then these are not even allowed. For high seismic zone, you cannot use flat plate, flat slab, wafer slab, or beam dash slab. You need to use proper frame system up to 15 floors if you're not using other lateral load resisting system, which we will talk about next lecture. So this is if you're trying to use your gravity system also for lateral load, these are the limits. Unless you separate your lateral load system from gravity load, then there's not a problem. This is now how you can mix system. This is categories of frames that you may or may not know. This is ordinary moment resisting frame, that means it has no ductility. It is very low reinforcement, normal. This is intermediate moment resisting frame, which has some ductility, some seismic detailing, some lateral load. And this is special moment resisting frame, which is specially designed to resist lateral loads and earthquakes especially. So if you have those kind of details, then as you can see here, that you cannot mix them together. Flat plate, you can only mix them with shear wall and brace system. You cannot use them alone in any of these systems. You must have a brace system or even not a dual system. So once again, this is a good metrics to show when can you combine the gravity load system with another lateral load system. So if you want to use flat plate, you must use shear wall system. That's the key. So if your building is based on 100% shear wall design, then you can use flat plate. Otherwise, you cannot use anywhere else. And then beam and slab, you can use almost everywhere. So this is the relationship. So these two tables are very important for you to choose the system. I'm not talking about only tall buildings. Any building system from, let's say, 4 floors to 20 floors, you can use these two tables as a guideline to start. For buildings above 30, 40 floors, the choices are less. But below that, you have all the choices available. And this table especially is quite useful. Now we have the structural part covered of all the systems. What are their requirements? What are their load carrying capacity? What are their span lengths? What is their applicability for lateral load? So this is quite clear now. All the information is here, correct? And now we go to the big picture concept that we need to combine this knowledge with other people who also need the floor system. We cannot make this. I told you that the decision cannot be made by you only. Other people also need to be asked, and they will affect your decision. So this is a big picture: architecture, structure, Then you have, appliances, materials, many things, landscape, energy efficiency, so many things will come into picture of the architecture and then structure. So this is the big picture concept of how you think of everything at the same time, or how you should think of everything at the same time, or how your decision will be affected. So from the architecture, you will get the plan. So from the building plan, restriction on height, floor usage, occupancy, cost limitation, building regulation, space requirement, they all have to be satisfied. Then structural requirement, basic requirement, occupancy, live load, wind load, earthquake, you use those tables that I just showed you. Then weather condition, restriction on total height, restriction on material, can use concrete or not, can use steel or not, can use post-tensioning or not, cost limitation, and design service life. This would be structural basic requirements. Planning requirement, building configuration, number of stories, span, length, column layout, whether it's uniform or not. This is the structural requirement. Then restriction on floor depth, slab levels, support system, and so on. Then construction requirement, construction, cast in place, precast, casting method, construction time will be very important now. So if this one is governing, system will be selected based on the construction time. And then owners, designers' attitude, availability of design tools. I mentioned to you, if you don't know how to design flat slab, it's out, right? And so on. If you don't know how to just design post-tension, post-tensioning is out, right? So normally post-tensioning, most engineers don't know how to design, so they give it to the contractor. So the contractors who do post-tensioning, they also do the design. And this creates a serious problem because now suddenly floor design responsibility is divided between two people. The original designer, structural designer, and the floor post-tensioning system designer. And so you say, okay, I'm designing this one, you're designing that. It's not a good situation. So the main designer must know how to design post-tensioning also, and then leave some detailing to the contractor, or at least check the design back. So that's another area that engineers need to learn. After that, you go to lateral load resisting system and then foundation. So foundation, lateral load resisting system, construction, planning, architecture, building, everything you need to think about making this decision, because this is one of the most important decisions in a structure. What floor system to use? Because everything will depend on that. The weight of the building, the mass of the building, the cost of the building, the time of the building will depend on the decision that you make for that. And it will be repeated so many times. So then I also talked about two things last time, and I want to give you a little bit few more slides on that. One is the multi-criteria decision analysis, or AHP, an analytical hierarchy process. I mentioned that this is a mathematical, semi-mathematical tool to make decisions about comparing systems, how to compare systems realistically, not just only on one criteria, multi-criteria. That's why we call it multi-criteria decision analysis, that there are multiple criteria like you see before. How do you put all this big picture thing into a framework where you can make a decision? Because everything must be part of the decision. How do you do that? What is more important? How important is that more important? How do you include that into the decision making and metrics? So this is just a summary of that. I mean, so basically we use this one. We allow the users to assign relative weight. So then you have to ask the client, what is more important to you? Tell me, what is the most important thing to you? Between cost and time, choose one. Between cost and aesthetics, choose one. So you do this pairwise comparison between everything, and you decide, okay, this is more important than that, this is more important than that. How much more important? Then you get weightage on the importance. And then finally, you have a weightage of everything relative to each other. And then you just compare them in that way. And then you weight, then you score each system based on that, and then you accumulate everything together in a simple. So this is the formula that you can use, that you can have multiple weights and multiple criteria. You keep multiplying them, keep adding them together. So you have 1, 2, 3 levels of criteria. You have, like, for example, structural criteria is one group. Maybe this is structural criteria. Within structural criteria, there is the strength, and the another one is, let's say, ductility. which is within that. So how important is structure compared to architecture, and how important is ductility compared to stiffness, for example? So you put those numbers here, then you multiply to the system, and then you add things together. So it's a multi-level, multi-criteria analysis of the choices that you have. And in the end, you just have a simple table like this. In Excel, Excel is, every time Excel is the final answer. You make an Excel sheet and you're done, right? So you put the system one, system, so flat slab, flat plate, beam slab, you put all the systems here, and then you say sub criteria one, item two, score, weight, score, weight, score, weight, you multiply, add it together, and you get one unique value of the system. Ultimately, you add and multiply everything, you get one unique value of the system, 95. Another system, 102. Another system, 200, right? Then you choose the system with the highest or the lowest number, depending upon how you put the things down. And it's as simple as that. And or you choose top three, and then you decide, or let the client decide. Okay, but you at least have a basis to do some kind of evaluation. So this is quite useful and quite important when you make decision which cannot be made simply because there are too many criteria to fill. So this connects the basic properties of the system versus various requirements versus big picture versus kind of a mathematical model. That's it.